Previously, the velocity was always, the slope of the velocity versus time graph would have been the same no matter where. The velocity was constant, so that any velocity versus time curve would be a straight line having the same slope. So previously, velocity was equal to the acceleration, which was constant. The rate of change of velocity was equal to the acceleration, and that was constant. Now, as we move into the water, we have to move water out of the way in order for the ball to accelerate, and we see that the ball doesn't accelerate quite as much. So we have less acceleration, and we expect greater velocity to further reduce acceleration. So that if we look at our direction field, okay, if we're not moving very fast, we probably will have a rate of velocity change that's pretty much the same as it was when we didn't have the water there. But if we allow the velocity to increase, and let's just look at several points where the velocity is a little bit greater, we expect to have a little bit less slope. We expect the velocity to change a little less quickly. And if we go to even greater velocity, we expect the velocity to change even less quickly, giving us a set of velocity versus time curves that are no longer straight lines. The faster we go, the more slowly we build velocity, because again, we're moving more water out of the way. Not only that, but there's another interesting thing about this situation, that the ball actually went deeper into the water, so that the position along the ramp the ball goes deeper as it moves along the ramp, so we got to take into account not only how fast the ball's moving, but where it is on the ramp. Now, in this case, if we just ignore the fact that the ball goes deeper as it moves along the ramp, we're going to see that v prime of t is a function of time and velocity. Okay, so that you need to know at least the velocity and perhaps the time in order to calculate this slope. It turns out that we really only need the velocity in this case. But in general, we see that we could get a differential equation where f is a function of t and v. Now this is a familiar situation. We can sketch the direction field, we can plot curves, and we can develop techniques for solving equations of this type. But the point is that this is another type of equation, and when we have a situation where the ball goes deeper as it moves along the ramp, we find that the rate at which the velocity of the ball changes is a function not only of t, but of position, which will designate by x, and velocity, which will designate by v. And this situation gets even more complicated. And we're not going to talk too much about this right now, but we will encounter situations of this type before too long as we move through the course.